Alright class, so there was a request to make a video for this sapling problem. I believe it's number 22. And I think that overall there's a few confusing things in this problem, but we should be able to, once we sort of clean it up a little bit, get through this problem pretty easily. We do have to use the quadratic formula on this problem, so I will show you sort of what that looks like and talk about how I solve that. Or you can just skip ahead at that point in time. But let's get started. And the first thing I'm going to do is basically just sort of try to interpret the words that are up here. First thing that I notice is that I've got partial pressures of these different values here. And right away I notice that I'm seeing torr, and that my answer here is going to be in terms of torr as well. And torr is just a unit of measurement for pressure. And even though we haven't used it to this point in this class, we could just sort of use it as if it was ATM or millimeters of mercury, just the same way that we always have. So this is at equilibrium. So right away I'm looking at this and I'm saying, oh, these are my equilibrium pressures. So I'm going to sort of think about this as in terms of a Kp. And earlier we talked about how Kp is just going to be the partial pressures of each piece, right? But we can use pressures instead of concentrations. So here I've got the partial pressure of PCl5, my products, over my reactants PCl3 over P, the pressure of Cl2. And these equilibrium pressures, that's what I'm going to put in for those different partial pressures. So it says 217 torr for PCl5, so on and so forth. I can fill that in. And if I do that calculation, I get Kp, the equilibrium constant, is 1.24. So this is really the first step in this problem. Solving, if we're given equilibrium concentrations for all of our pieces, right away you should think to yourself, oh, that means I can solve for a equilibrium constant. So in this case, we're going to call that a Kp since we're using pressures, and the value here is going to be 1.24. But we would do this calculation just like we would do any normal type of calculation. So the next part of this, it says some quantity of Cl2 is going to be injected into the mixture. So I'm going to add in, right, some Cl2, and the total pressure jumps to 263 torr. So at this point in time, we need to figure out, well, what does that mean in terms of how much Cl2 I'm adding in? I know that the P total, right, which equals 263, that's going to equal the pressure of PCl5 plus the pressure of PCl3 plus the pressure of PCl2, right? So the pressure of all of the individual pieces will equal 263. So I can just sort of do some math, adding all of these up, right? That's where we're at before. That's going to equal some pressure that was at before, and then we're just adding more Cl2 in order to get to 263. So the calculation that I would do 217 plus 13.2 plus 13.2. That's going to tell me the pressure that we were at before we added in more Cl2. So the difference there, 263 minus 243.4, 19.6. This is the amount of pressure of Cl2 that we're adding in. So we're adding in 19.6 torr of Cl2 to get to my final pressure here. So now what we have is we've got a new equilibrium that needs to be re-established. I've perturbed the system by adding in more Cl2, so the system is going to move, right? It's going to get back to equilibrium. So my initial pressures here for PCl3, that's still going to be my equilibrium that I had from before, 13.2. For Cl2, now it's going to be 19.6 plus 13.2, right? I've added it in. So now it's going to be 32.8. And then for PCl5, again, that's going to still be our 217. So these are my new initial concentrations. So we're not at equilibrium, right, because I've perturbed the system. So to get back to equilibrium, I'm going to shift this reaction to the right. I'm going to go from over here, I'm going to go to the right, and then I can write out my equilibrium expressions. 13.2 minus x, 32.8 minus x, and 217 plus x. So now the goal is to solve for x. Right, so the goal here is to solve for x. So I'm going to show you how I would do that on this other piece of paper. So at this point in time, we could say 1.24, our Kp value, is going to be equal to 217 plus x divided by 13.2 minus x over 32.8 minus x. And now if you have a fancy calculator, if you have a TI-89 for instance, you can just plug this into your calculator, say solve for x, you'll get the x values out. If you have a different way to solve this using a program or whatever like that, any way that you can solve for x at this point in time, that's great. If you do not have a fancy calculator or anything, we can sort of work this out algebraically. So I'm going to show you what I would do here. The first thing I'm going to do is distribute this bottom, two parentheses. So if I distribute this, I end up getting 432.96 minus 46x plus x squared. And it's going to be plus x squared because I've got minus x times minus x. That's going to give me a plus x squared. Then I would bring all of this up essentially. So 1.24 times 432.96 minus 46x plus x squared equals 217 plus x. And now I'm going to distribute the 1.24. So when I do that, I'm going to get 536.87 minus 57.04 x plus 1.24 x squared equals 217 plus x. And now the goal is to group things together, and I want one side to equal 0. So if I subtract 217x and 217 and x from each side, I will end up with 319.87 minus 58.04. Keep in mind that since it's minus 57 and we're minusing x, it becomes minus 58.04 plus 1.24 x squared equals 0. So now this is going to be my a value, this is going to be my b value, this is going to be my c value for the quadratic formula. So you can now either do the quadratic formula, or at this point in time, really for this class, if you want to practice that, that's great. But what I would do and what I've been doing when I solve these problems is just use a quadratic solver on the internet. Just type into Google quadratic formula solver, plug in your a, b, and c values. Here we're going to get two values for x. X equals 6.38 or x equals 40.4. So now at this point in time, we need to decide which of these x values we're going to use. So 6.38 or 40.4. So going back to my original problem, to choose which x value makes more sense or which one we're going to use, we're just going to look at our equilibrium concentrations and we're going to say, well, 13.2 minus 6.38, does that make sense? Does that give us a reasonable answer? Yes, it does. 13.2 minus 40.4, does that give us a reasonable answer? A negative concentration doesn't make any sense. Negative pressure doesn't make any sense. So choosing which x value to use seems pretty obvious to me. 6.38, that's going to be the one that we want to go with. I can then take that 6.38 and solve for my equilibrium pressures for all three of these gases. So 13.2 minus 6.38, that gives us a value of 6.8 here. For PCl2, I get a value of 26.4. And finally for PCl5, 223.4 or just 223, that should be my final answer using the x values that I calculated. So I'm not going to show that, but hopefully it makes sense. Just plug in your x value for your equilibrium concentrations here, and then you'll be good to go. So just to recap, this is a big problem. There's a lot going on. We've got to solve for our k value initially. We've got to use an ice table. Draw this ice table out. Draw this ice table out completely. It's easy to sort of skip steps here, but you're really going to benefit yourself if you draw this out completely. You know, you say it's going to go to the right. I know that because I've added in a reactant. Le Chatelier's principle says it's going to go to the right. These are my expressions for my equilibrium concentrations. How do I solve for x? Well, if I know Kp, then I can set that up and solve for x. Solving for x, here we had to use a quadratic formula. On the exam, you will not have to use the quadratic formula, but it is a good practice. You should figure out how to do it. Writing out all of this algebra to keep everything straight. A lot of easy mistakes here. So make sure that you're doing that and you're able to do that. All right.